So we have a poll about the things that are just discussed. And we just want to see if you understand a few basics. So I will show a question, and Chris has the poll question, and then we can immediately see if you have the right answer. Oh, sorry. So here we have such a biased common source stage. And it is biased in such a way. So the source, the signal source is VF, S, and RS. The load is RL, and we have VL across the load. But it is biased in such a way that the IGS and the VGS are adjusted exactly such that VDS equals 0.9 volt and IDS equals 0.1 milliamp. And now the question comes from quiz.
Okay, we have about 20 seconds left.
Oh, it's automatically cutting off or not?
Well, I'm the I'm the automaton.
Oh, you are the one who.
We have 81% of the votes. So
Come on, let's get to 100.
so I still need 7 answers. Okay, well let's have a look at the results.
And is the good one in between, Chris? Or I mean, can you show which is the good one? Or
No, I cannot show the good one. I can just show the answers that are given.
okay, well, if this was democracy, then
The
well,
good one
there's
would
no
have won because that
there
is
there's no majority, but still the 33% would have won. So nothing is happening. If you disconnect the source and the load, then the whole thing will just stay as it is. Let's see how this works. If here is 0.1 milliamp, and here is 0.9 volt, then here is 0 volt, and here is, oh, sorry, no current. This is just Kirchhoff, because all this 0.1 amps is flowing through the transistor. So if there is no current through the resistor and no voltage across it, you can just remove it and nothing will happen. And the same is here. If we have here VGS, then here is 0. And there is no current flowing here because this is exactly the current that it needs to generate this operating point. So this is also 0. So if we remove the source, nothing happens. And this, I thought I said this during the lecture. So it is on the video now, so you can watch it again. But this is the whole idea of this biasing. For any DC termination, you can leave it open, you can short it for any DC termination here. And here, the operating point is defined by these 4 sources. And of course, this is only valid for one temperature and one device, and that is the temperature and the device at which you have determined the VGS and the IGS to create this condition. Have I explained it clear now? Well, I don't know how you can say yes or no to me, but that's Chris will notice if you can lift your finger and say, yeah, so this is the whole idea of the biasing, to create an operating point that is insensitive for the termination of the port because we have 0 voltage and current conditions at this port. Yeah, so let's make it clean because my handwriting is horrible, and go to the next one. So we have a little bit change in the figure. Yeah, but again, the biasing is done in a way as in the previous condition. And now we have another question. So the question now is, which sources are delivering current?
Power.
Power, sorry.
Okay. Here are the results.
Okay, well, I'm glad to see that here 49% is okay. So the current source is the one who is delivering the power. Let's now try to see how that works. So I will do it in a similar way. We have biased the thing exactly as I told you in the previous exercise. So here the current is again 0.1 milliamp. Oh, what horrible writing, but okay. 0.1 milliamp, which means that all this current is flowing there and there is no current here. So here we have 0 current. So if there's 0 current, then this one is not delivering nor dissipating any power. And here we have a positive voltage plus minus of 0.9 volt, because this is the operating voltage that is stated in the text. So this is 0.9 volt, 0.9 volt. And if the current would go from plus to minus through the device, then it will be dissipating. But now you see the current is flowing from the minus to plus, because here's plus 0.9 and here 0. So plus minus, and the current is flowing the opposite way. So this one, the product of the branch current and the branch voltage is negative. So this one is the active source. This one is delivering power. Is it clear?
Let's go to the next one. Crystal clear, I see here.
Okay, so this is basically what you have to do is nothing else than just apply Kirchhoff's law and be very consequent in it. A positive product of branch current and branch voltage is dissipation, a negative is energy delivery. It's as simple as that. 112. I'm trying to make 112. I don't see my mouse. Oh, it's still on the drawing stuff. 112. So again, the same biasing situation with a little bit different sources. And now the question, Chris. It's the same question now.
It's the same question, but the circuit is different. So maybe there are different answers. I see a good trend.
Dat is leuk, zo'n poll.
Okay, 86%. So stop the counting and share the results.
Okay, well, we are just above the 50% now. The voltage source is the right answer. The voltage source is now delivering the power. Let us go again to this picture and see why it is as such. So the whole thing. Let's first find my mouse. So the whole thing is biased again at 0.1 milliamp for the drain current, and 0.1 volt, 0.9 volts, sorry, for the drain source voltage. And that is VDS, yes? Sorry, it is VDS that I'm indicating. So which means that here the voltage equals 0. And again, the current equals 0. And that's what we know because it's the quiescent operating point. We have selected this as such. Now you see, if there is no voltage across the current source, and you see there's 0 voltage across the current source, it doesn't deliver any power and it does not dissipate anything. So this one is now doing the job, the voltage source. The voltage source, the current is flowing, this 0.1 milliamp is flowing in this way through the voltage source. And it's flowing from minus to plus, which means that the product of the branch current and the branch voltage is negative. So this one is now delivering power. And you see there, so this is just again the same. it's like you take the product of the branch voltage and the branch current. If it is positive, there is dissipation. If it is zero, there's nothing. There's no energy delivery, no power delivery, and no dissipation. And if it is negative, then the source is delivering power. And for this, it is zero because the voltage across it is zero. And for this, it is negative because the current flows through the minus to the plus terminal through the device. So the branch current, product of branch current and branch voltage is negative. Yes, I hope it is clear. Are you recording this, Chris?
Yeah.
Okay, do you want to have this on Brightspace?
I will put it also on Brightspace.
Okay. Do we have more? I think we have more.
You have two more.
I have two more. So let's go for the next one. Now here, this one, number 113, and Chris will launch the question for 113.
Now, which sources deliver power when the input voltage source gives a voltage larger than zero?
So the input voltage source is now larger than zero. And which one is now delivering power at the output? Yes, that's the question. Output bias source.
Okay, I'll end the polling. Let's see the results.
So it's still running, I see.
Yeah, but now not anymore. And I see there's a question.
Is the question asking for delivering power to the load or delivering power as dissipating? I don't understand the question. Is the question asking for delivering power to the load or delivering power as dissipating power in general? Chris, begrijp jij hem?
Can I explain it?
Yes, yes.
I was thinking, is it asking for the power being dissipated in the load, in the load resistor, or just in general if there's power being dissipated or not?
For this question, it's power, which output bias source will dissipate power or deliver power?
Okay, so it doesn't have to be in the load resistor.
No. Let's say from the previous questions, as we were still in the quiescent operating point and the voltage across the load was zero and the voltage across the source was zero, there was no power in the source and in the load.
Yeah, so yes, exactly.
And in this situation, it might be different.
Yeah, there is power. Yeah, okay.
Yeah, because now we have a signal. So let me explain this situation. So now we have a signal and we have a slightly, what was a slightly positive signal here, yes? So this is plus and this is minus. So we know that, I hope you know the MOSFET characteristics, that if you increase the gate source voltage of an N-channel MOSFET, that the IDS will now become larger. It will increase, so it will be larger than 0.1 milliamp. Yeah? So 0.1 milliamp is provided here. So the rest will be provided through this path because Kirchhoff's laws should apply. So here I have current and here I have current. Now, let's say here we see that the current is flowing. This current, this output current is now flowing from the negative terminal to the positive terminal. So this one is definitely delivering power, this bias source. So this one and this one, well, even if you would drive a lot of positive voltage, the voltage across the MOSFET will probably never become exactly zero. It will always remain a little bit positive because there's flowing current through it, and the on resistance of the device will not become zero. It will be maybe 1 microohm, but there will be always a positive voltage. So it means we have positive VDS for this situation, but the current here flowing from the minus to the plus. So this one will also deliver power. So the good answer is 48%. Both output sources are now delivering power. So as you have seen before, this one didn't do anything in this situation, and now it starts delivering power. And this one did a lot. It did 0.1 milliamp over 0.9 volt, and now the voltage drops. The current is still the same, so this one is going to deliver less power. So this one less power, and this a little bit more power. But there will be power at the output as well, but that has not been asked. Yes? So the answer to the question is both sources are now delivering power. I hope it is clear. Shift. Up. Now we have another one, I guess.
The last one.
Again, we are in the quiescent operating point, and now the question is...
What happens if the input supply voltage is lower than zero?
The input source voltage, sorry.
Source voltage, yeah. Okay, I'll end it and share the results.
So the result is 56% positive. Let's see what is going to happen in this case. And I always have to look at my pen. So here we now have a negative input voltage, so it will be minus, plus, which means that the transistor is conducting less current, so there will be another current flowing a little bit through the load. And if the current is flowing through the load, then eventually in the quiescent operating point, there was no current flowing through this voltage source because there was zero voltage there. But now there will be current flowing through the load, and the current flows in this way. So from plus to minus, so this one will dissipate power and not deliver. And this one says it has a positive and negative voltage here. The voltage will even increase because the transistor is turning off, and the current is still 0.1 milliamp. So it will deliver more power than before because the product is still negative. The current flows from the minus to the plus. So the product of this voltage and current is positive. Oh, sorry, I'm seeing, I touched something and I was doing 115, 13. Sorry for this, guys.
115.
I have to do it again. But now you have another story as well for 100 for this one. And this is a different story, of course. Let's clean it up. Thank you for making me, for letting me attend this. So now a negative voltage, which means that the transistor will turn off, which means that the current will, well, if there is still a little bit current through the transistor, it will flow like that from minus to plus. Let's say the transistor doesn't turn off completely, then there's still power dissipation here, although it decreases with decreasing the input voltage. And here we have now, we originally had no voltage, but now we have a positive voltage here. And you see it is flowing from minus to plus through the device. So this is delivering now power. So it means both are delivering power. So 57% is okay. And if you would like to have the details, it's going to tell you that this is going to deliver more power because its voltage is increasing and the current is still the same. And this one is delivering less power because the current is decreasing while the voltage is still the same. So I hope at the end I did it correct anyway.